Hi everybody, it's been quite a while since I posted an update on this power logging project, and quite a lot has happened. Some of it interesting and some, well, challenging. So first of all, I left off the last video looking at some of the noise issues, and I've done something about that. We're going to look at that today, but we have also implemented some new workarounds to some issues that we anticipated, and as well as run into some big problems. So that's going to be our video today. Now you remember in our last video we went and put some additional capacitors, and you might not be able to see it quite as clearly, but they are here all over this power buses, all over the place. Really, I added a lot, and it turns out that it's really difficult to get rid of some of this noise. I'm going to maybe put this, not sure you can see this in focus, but there are many, a whole string. I put a lot of caps here, and on this side I put big caps, small caps, electrolytic caps, polyester caps, all over the place. On top of that, I've also added some inductors on the power line to the op amps, just to get rid of the noise, and others elsewhere, right? So quite a bit of things. I reconfigured the bus a little bit. Very difficult to isolate noise. I was able to reduce it to some extent, but there's still noise problem, spikes coming out from the really stemming from this ADC. Right, so the sampling action of the converter creates a lot of noise. So that's one part of the problem, and those of you who are attentive might notice we've got something extra here. Right, we're going to talk about this in a little bit, but basically what this is that this is a full wave rectifier. Now you remember that in our last couple of videos ago I talked about how these op amps here, basically what they do is they clip off the negative going cycle of the AC the AC voltage that we are sampling, and it only measures the positive going cycle. So effectively these are half wave rectifiers, and then what it does is it samples it, and these capacitors here, they are sample whole capacitors, right? So basically we get the peak, and then we feed that peak into this through a buffer. This is dual op amp, and through the second op amp, which is basically just a buffer, it goes to the ADC. So we capture the peak, and so basically now you have a smoothing of the half wave rectified signal with these caps, and because of that we had ripple issues. I think we did look at some of the ripple, and I was concerned about that. And then I came across this really interesting circuit down on the LinearTech website, and basically what it is this op amp is dual. This is a quad op amp pack, because I was running out of space on the board. But basically what this is a full wave rectifier without the problems with the diodes causing the voltage drop. So it's a very clever way they did this, and let's look at the tech sheet for this, the data sheet. So I came across this particular circuit on LinearTech's website, and this is a very clever circuit. Look at this. They've got these two op amps, and they've got it hooked up just so that the signal, the AC signal, comes in on this input here, right? It goes to the negative, the inverting input of this first op amp, and it gets flipped over. So you have a negative going pulse here, it gets flipped positive, right? So it goes right through this diode and appears at the input, at the non-inverting input of the second op amp. Okay, just think about that. Negative pulse flips, appears here. What happens with the positive going pulse? Well, the positive going pulse gets flipped into the negative, but then this diode blocks it. So effectively this circuit will only allow the flipped negative going cycle to pass through here. When you have the positive cycle, you basically flatline, right? And they've hooked it up so that the gain of this bit here is 1. Now what happens then to the positive going cycle? well, that goes right through these resistors, and frankly 200k plus 400k is nothing compared to the high impedance of this, usually the very high impedance of the input. So these resistors appear like they're nothing, right? So the positive going cycle goes right through here, because the negative going cycle, when it comes here, it just gets blocked, because this is a single rail op amp, so it goes nowhere. And between this guy flipping, you actually end up with this full wave rectification without having to worry about voltage drop through diodes. Very clever. Now you might be wondering, what about the voltage drop over this diode? Well, the way this amp is hooked up, the amp will compensate for any loss here. It just ensures that the input and output are matched. So this is a very, very clever circuit, and I thought, well, why don't we give this a try? Alright, so I've basically built up the circuit on this breadboard here, and so this is a quad op amp pack. We are just using the left half, and essentially this is what we saw early on here. Instead of using the 200k, I use 100k because that's all I had. The actual values is probably not so important, whether it's as long as it's not like in the mega ohms. So I think this probably works quite alright. 100k with that 1N4148 diode here. So I've powered this up, and let me get the power going here. And I've also now fed in the input on this yellow wire. You have the I've got a AFG, a frequency generator here. Then I'm going to put a sine wave here, and then the output comes on this orange wire, right? So on the scope, this the yellow trace, that's the power for the well, that's the yellow trace is the input, and the blue trace is the output. I'm going to power on the circuit right now. Okay, so we have 5 volts now going into this circuit. This is single-ended. The amazing thing is that this guy can handle the negative going cycle. I'm not quite sure how they did that, but it works. Okay, so I'm going to turn on the I just turn on the now you can see this. All right, I'm going to turn off the blue trace first. This yellow trace that you see here, that's the input. That's going in here, right? Now just kind of move to one side, and hopefully you can still see it. So this here is the input, and if we were to trace the output, and let me just take the we'll put on the blue trace now. If we traced it at the output of this, you can see basically what this does is it's mixed that up. I can't just see half of it, unfortunately. Can I? Maybe I can get half of it just at the output here. Yep, there you go. Okay, so that's just the first op amp at work. It flips it, and then on the positive going cycle, it blocks it, right? But then it gets mixed back over here, and what you see then is this amazing output, which combines to this brilliant. I actually think it's brilliant. So let me just try and let's just play with the amplitude a little bit and see where we go with this, right? So this is about as high as we can go, but just kind of scale it down. You see it works beautifully. I'm amazed. I actually had some some problems with the circuit board layout initially, but I've kind of corrected that. But this works beautifully. Look at that. That is exactly what you would expect, right? The blue trace, right? This is a yellow trace here, and the blue trace just does that. I mean, part of the problem we're seeing with that yellow trace and the sound is that not triggering properly. I should really do something about this trigger. Just make sure it triggers. I don't know. Maybe yeah, that works better. Okay, so that's what you're basically seeing. It's just I'm just gonna freeze this. Come on. Okay, so I think this is the circuit that I've implemented on the board here with this little, not sure you can see this, but this little bit of space here. I put one of this in place, so I'm going to turn off the power for this thing now. Let's see how to turn off the power. Off the power. Okay, power's gone. Okay, so well, I did that, and I've also hooked this up to the transformer. So now we are actually measuring successfully through this whole circuit, through this full wave rectifier, and then through the peak capture. We are actually successfully measuring the voltage of the mains. Now you might wonder what kind of problems. Well, there are several problems we had with this thing early on. First of all, software wise, there were quite a lot of bugs in the SQL library I was using, and I think I pretty much worked out all the bugs that are relevant to us anyway. So that part is done. There's still some problems whenever you do interrupt driven stuff in relation to the TCP library, so in regards to the ESP8266. So let's go and see what other problems we have, because we do have a lot of other problems that we need to talk about. Okay, well, this is the telnet interface that I've implemented. You can see how I've got some basic display going on. So I'm actually accessing this board. I thought I'd just show you real quick over the network and over Wi-Fi. So you can see it samples every 2 seconds. It'll take some kind of sample, and you can see over here at ADC volts, we're actually getting a reading of the mains voltage, right? And then every minute it will provide an average volts. The amperage side, we have not really gotten into that, but this works. I've also done a couple of things. I've got some variables that I can change, multipliers that I can change. I can type this and I can get things going. So there are a couple of things I can do down here. This is very convenient for me because it allows me to fiddle with it, settings, while I'm trying to get this thing working. So this is what we've been doing a little bit in addition to fixing up the bugs. All right, now so far so good, but we have problems, as I was saying. Well, the during this time the current sensor came in, and I thought I'll show you what the current sensor looked like. All right, well, if you look at this is actually the current sensor, and I've got it clipped around the neutral cable on the switch box, right? I should get you a better view of this. So this now comes down on the cable, and the way they've provided it is it comes in on the, sorry for the warm light, but it comes in on this usual 3.5 mm jack, which I've got connected. I've got a 1 kilo ohm resistor, and I've got it connected over here to my fluke, which I've been kind of monitoring for a little bit to see how well that works. So you can see right now it's measuring 2.39 volts over it. So all this while I've been thinking, well, this is very good. All I got to do is just put that through my full wave rectifier, capture the peaks, and then we can assume that we have something going on. Actually, why don't I just turn off the power turn off the switch to the lights, and you can see that that's gone down to 2.2 now, right? So it's actually quite responsive. Well, that should have worked nicely, all right? That shouldn't have been a problem, but we do have a problem, because then I decided, why don't I take a look at the signal that we have with the scope, right? Which is exactly what we're going to do right now. Okay, give me a minute to hook this up, and then we'll be right back. All right, so now we have this, at my point I've connected that now to the scope, and this is what we are looking at on the scope. Look at that. That does not look like a sine wave, does it? I mean, we've been assuming that all along, that our calculations, let me just turn off the power to this switch, this light. You see, it changes, right? So you see the change, but it's not a sine wave. We had been assuming all along that mains would be a sine wave. I mean, in every textbook and example you see concerning the mains, you almost always see a sine wave, but this is not a sine wave. And that is exactly where our problem is. If it's not a sine wave, you can't just capture the peaks like that. You're not going to get a correct value. You need some way of calculating the actual RMS, and this is exactly our problem. I have to rethink how we're going to do this, and I have an idea of how to go about it, but it does mean that I'm going to have to redo quite a bit of the circuit. I can't just measure the voltage and kind of do it like that. I mean that would be really convenient if that's possible, but unfortunately we're going to have to find a way to deal with this now. So that's where we are with regards to this whole thing. And the solution, I think, to that problem may have to be something like this. This linear tech part, LTC1966, it's got this little chip, runs off single rail, takes the input and it outputs RMS voltage, DC. This looks like exactly what I need. There may be a few caveats, but I'm going to order this part, and in some future episode of this we shall see what this implementation looks like, and if this is going to work for us. But basically we're going to have to make some modifications. The same thing applies to the voltage as well. I scoped the mains voltage and it's not exactly a sine wave. I don't know what made me think that it would be a sine wave all along, as a post assumption and all the textbooks that you've been looking at. But yeah, it's not a sine wave, and it's a little bit more involved getting the RMS value from that, right? So this is a very interesting circuit that we are looking at. So that's what I'm going to order, and hopefully we can get something here going. It's got different configurations that you can run on, whether it's a split rail or a single rail. And basically what we would need for it to do for us is single rail, and you may have to find some ways of scaling it so that this all works nicely. I'm going to order it. It comes in an MSOP package, so that's going to make it a little bit hard to prototype, but I'll get the prototyping boards and all that, and that's part of it. All right, so that's with the problem that we have had, and I've done some other work as well. In the next update we'll see what else I've done. Okay, see you all.